Right now, warm water off the coast of Africa is feeding a chain of storms. One of them could grow into a monster within days. You live near one of the most exposed coastlines on Earth, and most people never notice the danger until it is almost too late. Every year, one 10-day stretch on the calendar carries more hurricane risk than any other point in the season. That window is closing in right now. In the next few minutes, you will travel inside a storm strong enough to double in power while a city sleeps, stand under a wall of ocean water taller than a 2-story house, and relive the final hours before 3 of America's deadliest hurricanes struck land. If stories like this pull you in, hit subscribe. It helps more than you think. 10 days, 1 coastline. Prepare yourselves, we begin. Somewhere off the coast of Africa, a cluster of thunderstorms drifts out over open water, and nobody on a beach 3,000 miles away even notices. Right now, in late August, something is stirring far out at sea. Every year, people who study hurricanes watch the calendar the way a lifeguard watches the horizon. They know a handful of days carry more danger than the rest of the year combined, and this year that stretch has already begun. Here is why this matters to anyone living near the water. Hurricane season officially runs for 6 months, starting in June and ending in November. Almost none of the season's worst storms show up on the first day or the last day. They cluster together in a narrow window in the middle, when the ocean has spent an entire summer soaking up heat, like a sponge left out in the sun. Picture a swimming pool in July. Early in the season, the water still feels cool from spring. By late August, that same pool feels like a warm bath, because months of sunlight have built up inside it. The ocean works the same way, only on a much bigger scale. It takes an entire summer for the surface of the Atlantic to reach its hottest point, and hot water is the fuel a hurricane needs to grow strong. That is why the days ahead matter so much. The ocean is now close to as warm as it will get all year, right as the upper atmosphere still holds enough energy to build a monster storm. Add those 2 things together, and you get the single, most dangerous stretch on the entire hurricane calendar. Millions of people live along the coast from Florida all the way up to Maine, in cities and small towns built close against the water. Most of them go about their day without a single thought about what might be forming thousands of miles away. But the storms of the next 10 days could decide whether this becomes a quiet, forgettable stretch of summer, or a chapter people remember for the rest of their lives. Every hurricane season tends to produce one storm that changes everything for somebody. Sometimes it forms early in the year, sometimes it forms late. But nearly every storm that has ever devastated an American coastline was born inside this same narrow window of the calendar, when conditions briefly line up in a way they do not the rest of the year. Scientists cannot yet tell you the name of this year's storm, or exactly where it might strike land. What they can tell you, with real confidence, is which stretch of days gives a storm the best possible chance to become something historic. That stretch has now arrived, and it will not fully pass for weeks. Somewhere out past the horizon tonight, warm water is waiting. High above it, wind patterns are quietly lining up. All a storm needs now is a spark, and the ocean has been building toward this moment since the very first day of summer. Nobody chose these 10 days. The planet did, through nothing more than sunlight, ocean currents, and the tilt of the Earth itself. Once you understand why this window exists, you will never look at a calm, blue summer ocean the same way again, because calm water can be quietly building towards something enormous underneath the surface. Mark one date in your mind, September 10th. Out of every single day in the year, people who study hurricanes have found that September 10th carries the highest chance of a storm spinning somewhere in the Atlantic Ocean. It comes from studying more than a century of storm records day by day, one at a time, the same way a scientist might study anything else that repeats. Think about it the way you might think about a birthday chart at school. If you lined up every student's birthday across a full year, some days would end up with more birthdays than others, just by chance. Now imagine building that same kind of chart using every hurricane ever recorded in the Atlantic Ocean since record-keeping began. When researchers actually did this, one date stood taller than every other day on the chart, September 10th. But compared to what comes next, a single date is only the beginning of the story. The real danger stretches across the 2 or 3 weeks wrapped around it, when ocean heat, calm upper winds and storm-friendly patterns all overlap at the exact same time. Forecasters call this stretch the peak of the season, and right now, the calendar is sliding straight into it. Here is the part that should genuinely get your attention. Almost every legendary hurricane in American history, the ones people still talk about decades later, formed somewhere inside this exact window. Storms that flattened towns, storms that reshaped entire coastlines, storms that are still studied by forecasters in training today. All of them arrived during this same narrow stretch of the calendar, almost like the ocean itself keeps a schedule. Why does the timing line up so perfectly? A hurricane needs 3 ingredients working together at once: hot ocean water, moist air rising off the surface, and calm winds high above the storm that do not tear it apart while it tries to grow. Early in the summer, the ocean has not finished warming up yet. Late in the fall, cooler air starts sliding in from the north and breaks the pattern apart. Right in the middle sits a short stretch of time when every ingredient lines up at once, like 3 green lights on the same street corner. That is the exact stretch we're entering right now, this week, on this coastline. For the people who track hurricanes for a living, this period is treated with a kind of quiet focus rather than panic, the same way a surgeon concentrates harder during the most delicate part of an operation. Every satellite photo gets checked twice. Every tropical wave rolling off the coast of Africa gets a second, closer look, because any one of them could be the storm this year is remembered for. Somewhere out over the ocean tonight, the next candidate for the history books may already be taking shape, unaware of the date on the calendar it happened to be born into. It has no idea it just walked into the most dangerous stretch of the year, and neither yet does anyone standing on the coastline it might eventually reach. Every year this pattern repeats with eerie precision, and most people never learn it exists until a storm is already bearing down on their town. Understanding this window is the first step toward understanding everything that comes next, because once you see the pattern, you start to understand why some years bring quiet beaches and other years bring headlines that last for decades. Slide your hand into the ocean water off the coast of Florida right now, and it would feel almost like bath water. That warmth is the single most important ingredient in this entire story. A hurricane is essentially a giant heat engine. It pulls warm, moist air up off the ocean surface, lets that air cool and release its energy high in the sky, and uses that released energy to spin itself faster and faster. Take away the warm water, and the entire engine stalls out. Here is the number that should catch your attention. Scientists measure ocean heat down to depths of over 100 feet, because a storm can churn deep water up toward the top as it passes. In large stretches of the Atlantic and the Gulf this year, that deep reserve of heat is sitting well above the long-term average, meaning the fuel tank is running unusually full for this point in the season. Think of it like a car with a much bigger gas tank than usual. A normal storm might run for a week before weakening. A storm crossing water this warm all the way down has the fuel to keep running longer, travel farther, and hold on to its strength closer to the coastline instead of fading out over open water like storms often do. But compared to what comes next, warm water by itself is only half the equation. Heat alone does not guarantee a monster. Some of the warmest years on record have still produced fairly quiet hurricane seasons, because other ingredients did not cooperate. Warm water simply raises the ceiling on how strong a storm could become if everything else lines up behind it. This is where the danger becomes personal for anyone near the coast. A warmer ocean means storms that intensify faster, storms that hold their strength longer after landfall, and storms that carry more moisture, which later falls as flooding rain hundreds of miles inland, long after the wind has died down. Researchers who study past hurricane seasons have found a clear pattern connecting unusually warm ocean years to unusually destructive individual storms, even in seasons where the total number of storms was average or even low. It is about how strong the worst one becomes, far more than how many storms form in total. That is the quiet danger hiding underneath this year's warm water. It may not produce more storms than usual. It only has to produce one storm capable of pulling every degree of that extra heat straight into its own engine and turning it into wind, rain, and rising water aimed squarely at a coastline full of people who have no real idea how much fuel is sitting just offshore, waiting. Imagine 2 campfires. One is built with a handful of dry twigs, small and easily managed. The other sits beside a stack of split logs soaked in kindling, ready to roar the moment a spark lands on it. Both are technically fires. Only one of them has the potential to burn out of control within minutes. Right now, the ocean along much of the East Coast looks a lot more like that second fire, quietly stacked and waiting, than like the smaller, safer version most people picture when they hear the word summer. Far off the western coast of Africa, hot desert air spills out over the ocean, and something invisible begins to stir. This region has earned a nickname among people who study storms. They call it the Hurricane Factory, and the name fits better than almost any nickname in science. It is a stretch of ocean where thunderstorms clump together, spin slightly from the rotation of the Earth itself, and sometimes grow into the exact same kind of storm that later threatens the American coastline thousands of miles away. Here is how it actually works, explained simply. Hot air rises off the desert and drifts out over the Atlantic Ocean as a cluster of thunderstorms called a tropical wave. If that cluster stays over warm enough water, and if winds higher in the sky stay calm enough not to rip it apart, the thunderstorms start feeding off each other. Warm, moist air rises in the center, cooler air sinks around the edges, and slowly, almost like a spinning top finding its balance, the whole system starts to rotate. Picture stirring cream into coffee. At first, the cream drifts in loose, disorganized swirls, but keep stirring in one direction, and eventually the swirls line up into a single, tight spiral. A tropical wave behaves the same way over days instead of seconds, organizing itself from a messy cluster of storms into a defined, rotating system with a center. Most of these clusters never make it that far. Out of dozens of tropical waves that roll off Africa every single hurricane season, only a small handful ever survive long enough to become a named storm. Dry desert air, cooler patches of ocean, or unfavorable wind can kill a developing system within days, sometimes within hours. But the ones that do survive carry something the others never developed: a clear, rotating center, low enough air pressure to keep pulling in more energy, and enough organization to keep strengthening on its own, almost like a snowball rolling downhill and gathering more snow with every turn. This matters enormously for the East Coast, because storms born in this exact factory, way out near Africa, are the ones with the longest runway. They can spend a week or more crossing open ocean, soaking up warm water the entire way, arriving off the American coastline already massive and already dangerously organized, rather than forming suddenly and close to shore with almost no warning at all. Right now, forecasters are watching this stretch of ocean the way a fire lookout watches a dry forest during a heat wave. Every cluster of thunderstorms gets a number, a percentage chance of development, and a satellite photo taken every few minutes. Somewhere inside one of those photographs, completely unnoticed by almost everyone on Earth, except a handful of meteorologists, next week's biggest story might already be quietly spinning itself into existence. Forecasters call these early clusters invests, short for areas worth investigating, and during peak season the factory rarely sits idle for long. It is common to see 2, 3, even 4 separate systems tracked at once, each given its own percentage chance of becoming something dangerous within the coming days. Most fade quietly into nothing, dissolving back into ordinary rain clouds without ever earning a name. But the factory only needs to succeed once every few weeks to change the entire story of a hurricane season. And right now, in the heart of this 10-day window, it is running at full capacity. 8 days before it ever touches an American beach, a hurricane can be born as nothing more than a ripple of clouds near the coast of Africa. These storms carry a specific nickname among forecasters: Cabo Verde storms, named after a small island nation off the African coast where many of them first take shape. And history has shown, again and again, that these are often the storms people remember longest, because they have the most open ocean and the most time to grow into something enormous before anyone on land even knows their name. Here is why distance actually works in a storm's favour. A hurricane needs warm water and calm upper winds to strengthen, and the open Atlantic Ocean, far from any interfering landmass, often provides exactly that for days at a time. A storm crossing thousands of miles of open water is like a runner given an entire empty track instead of a crowded hallway. Nothing slows it down, nothing disrupts its rhythm. It simply keeps building, day after day, mile after mile. Compare that to a storm that forms suddenly closer to the Gulf Coast or the Caribbean. Those storms can still turn dangerous, sometimes shockingly fast, but they typically have less open water and less time to organise before reaching land. A Cabo Verde storm, by contrast, might spend a full week or longer crossing the Atlantic, strengthening the entire way, arriving off the coast already carrying the kind of raw power that took days to build rather than hours. Some of the most catastrophic hurricanes in American history began exactly this way, as a small, disorganised ripple of thunderstorms near Africa that nobody outside a weather office had ever heard of. By the time those same systems approached Florida, the Carolinas, or the mid-Atlantic coast, they had grown into fully mature hurricanes carrying weeks of accumulated ocean energy inside them. This is part of why the 10-day window matters so much right now. Peak season is exactly when conditions across the entire tropical Atlantic tend to favour these long-track storms the most. Warm water stretching almost uninterrupted from Africa to the Caribbean, and calm upper winds allowing a storm to organise early and keep organising the whole way across. Somewhere out past the Cabo Verde Islands tonight, in water still lit faintly by a setting sun, the next storm on this year's list may already be gathering its first thunderstorms together. It has more than a week of open ocean ahead of it, and every single mile of that crossing is another chance to grow stronger before it ever reaches a coastline full of people who will not hear its name until it is already halfway across the ocean and already far larger than it was on the day it was born. There is something almost unsettling about the math involved. A storm crossing the full width of the Atlantic Ocean covers a distance roughly equal to driving from New York City to Los Angeles and back again, only across open water, with no land to slow it down, and nothing but warm ocean the entire way. By the time it finally reaches the Caribbean or the edge of the United States coastline, it has had more time to strengthen than almost any other type of storm on Earth, which is exactly why this particular birthplace deserves so much attention during these 10 days. A disorganised mess of clouds is just weather. The exact same system, 12 hours later, spinning around a defined centre, is suddenly something with a name, a number, and a warning attached to it. That transformation follows a strict, specific set of rules that forecasters apply the same way every single time, anywhere in the Atlantic Ocean. A cluster of thunderstorms only earns the title of tropical storm once it develops a clear, closed circulation around a centre of low pressure, and once its sustained winds reach at least 39 miles per hour. Cross that line, and the system stops being just weather. It becomes a storm with a name. Names are not chosen at random in the moment either. Every year, the World Meteorological Organization keeps a preset alphabetical list ready in advance, cycling through letters from A to W, skipping a few rarely used letters near the end. This year's list includes names like Arthur, Bertha, and Cristobal, already waiting in order, long before anyone knows which storm will actually claim each one. Here is why naming a storm matters far more than it might seem. A name turns an abstract weather system into something the human brain can actually track and remember. Studies on public safety have found that people pay closer attention and respond faster to warnings once a storm has a name attached to it, compared to a nameless system labelled only with a number or a percentage. Think about the difference between hearing there is a 40% chance of a storm forming near the coast, compared to hearing that Hurricane Diana is now approaching your town. One is an abstract statistic, the other feels like it is coming for you personally, and that emotional difference can be the reason someone chooses to evacuate in time, instead of waiting until it is too late. But a name is only the beginning of a storm's identity. Once a system strengthens further, crossing 74 miles per hour in sustained wind, it graduates again, this time into a full hurricane, and gets sorted onto a 5-step danger scale based purely on wind speed. From there, everything about how the public views that storm changes almost overnight, from a curious mention on a weather app to a headline running across every news channel at once. Somewhere in the Atlantic tonight, a swirl of thunderstorms may be crossing that first invisible line right now, quietly becoming a tropical storm before a single television station has mentioned its name. Within days, that same name could be spoken by millions of people all watching the same radar screen, waiting to see exactly where it turns next. There is something oddly personal about the whole system, considering it was designed decades ago purely for practical reasons. Early forecasters found that using numbers and coordinates to describe multiple storms at once led to confusion among sailors and coastal residents trying to track more than one system in the same week. A name is short, memorable, and impossible to mix up with anything else in the sky. It also means that decades from now, long after this year's headlines fade, a single word spoken quietly will still be enough to bring back the exact memory of what happened along this coastline. This year, before hurricane season has even reached its official peak, ocean temperature charts are already showing lines that climb higher than almost anything on record. Scientists who track ocean heat use decades of satellite and buoy data to build an average for every single day of the year, then compare each new measurement against that long-term baseline. When this year's numbers came in, large stretches of the Atlantic and the Gulf were sitting well above where they should be for this point in the summer, in some areas by a wide enough margin to stand out clearly on the chart, rather than blending into normal yearly variation. Picture a thermometer at a doctor's office. A single degree above normal body temperature might not worry anyone, but several degrees above normal, held steady for weeks at a time, is the kind of reading that gets immediate attention. Ocean temperatures work on a similar principle. A small rise barely changes anything. A larger, sustained rise across a huge stretch of ocean can be the difference between an average storm and a historic one. Here is why this particular year has caught the attention of so many researchers. Record ocean warmth alone does not guarantee a busy season, because other ingredients, like wind patterns high in the atmosphere, also have to cooperate. But when record warmth does combine with favourable wind conditions, even briefly, the results tend to be dramatic rather than mild. Some of the most destructive individual hurricanes in modern history formed during seasons that were not even considered especially active overall. That is the uncomfortable truth hiding inside this year's numbers. Total storm counts might land close to average, or even below it. But the raw amount of energy available in the water, if a storm manages to tap into it directly, is higher than it has been in years, which raises the ceiling on how strong any individual storm could become if the timing lines up. Researchers studying long-term ocean trends have also found a consistent pattern connecting warmer years to storms that intensify faster and hold their strength longer, sometimes staying dangerously powerful right up until the moment of landfall, instead of weakening the way many historic storms did while still over open water. For the millions of people living along the coast right now, this record warmth is invisible. Nobody can see it by looking out at a calm, blue ocean on a sunny afternoon. But underneath that calm surface sits an unusually large reserve of stored energy, quietly waiting for the right storm to come along and pull every bit of it upward into the sky. Fishermen and coastal scientists sometimes describe this feeling in similar terms. They talk about water that feels wrong for the season, warmer than memory says it should be, holding its heat later into the year than it used to. That lived experience lines up almost perfectly with the satellite data, two different ways of measuring the same uncomfortable truth about the ocean off the coast this year. This record warmth alone guarantees nothing. The ocean has run hot in past years without producing a season anyone remembers, and it could do so again, but the raw energy currently stored in the water gives any storm that forms this year a taller ladder to climb than storms have had in a long time, and how high any one of them decides to climb that ladder remains the one question nobody, not even the scientists watching the charts most closely, can yet answer for certain. Far above the Pacific Ocean, a slow shift in water temperature thousands of miles away is quietly fighting for control over what happens on the other side of the world along the American East Coast. That shift has a name, El Niño. It describes a periodic warming of surface water in the tropical Pacific Ocean, and even though it happens an entire ocean away from the Atlantic, its effects reach across the whole planet. During strong El Niño years, wind patterns high in the atmosphere over the Atlantic tend to become more hostile toward developing hurricanes, slicing across the tops of storms before they can fully organize. Here is the piece that makes this year so unusual. Normally, when El Niño shows up strong, it wins the fight decisively, and hurricane seasons tend to stay quiet as a result. But this year, El Niño is facing an opponent it does not always face at full strength. Record warm water sitting directly in the Atlantic and the Gulf, close enough to the coastline that a storm could develop nearby, with far less time and far less distance to travel before reaching land. Picture a tug of war between two teams of very different size. One team, the wind shear from El Niño, usually wins by pulling storms apart before they can grow dangerous. The other team, the unusually warm water sitting close to home, is pulling just as hard in the opposite direction, trying to give any storm that does survive an unusually powerful boost right as it nears the coast. This is exactly why official seasonal forecasts this year describe conditions as complicated rather than simply calm or simply dangerous. The overall number of storms may end up lower than a typical year, because wind shear will likely prevent many systems out over the open ocean from ever fully organising. But forecasters have specifically warned that any storm that does manage to survive that hostile wind pattern, especially one forming closer to home, instead of crossing the whole ocean, could intensify unusually fast, precisely because the water waiting for it is so warm. In other words, this may not be a year defined by how many storms form. It may be a year defined by one storm that slips through the wind shear at exactly the wrong moment, over exactly the wrong patch of overheated water, close enough to the coastline that there is very little time left to prepare once it finally breaks free of El Niño's grip and starts pulling in everything the ocean has been saving up for it. Forecasters have a phrase for this kind of season, one that shows up quietly in official outlooks without ever making the headlines it probably deserves. They call it a low-confidence, high-impact scenario. It means nobody can promise how many storms will form, but everyone agrees that if the wrong one manages to slip through, it will not arrive as a gentle warning. It will arrive as the one storm this entire season is remembered for. This is part of why seasonal forecasts should never be mistaken for a promise of safety. A below-average season on paper has produced some of the costliest single hurricanes in American history simply because it only ever takes one storm finding the right gap at the right moment. Right now, over these 10 days, that gap is exactly what every forecaster on the Atlantic coast is watching for, hour by hour, satellite pass by satellite pass. Thousands of feet above a growing storm, an invisible force is deciding its fate, and almost nobody watching the ocean below can see it happening. That force is called wind shear, and it describes a simple idea with an outsized effect. It happens whenever wind speed or wind direction changes sharply between the surface of the ocean and the upper atmosphere. A storm needs to stack itself neatly, like a tower of blocks, with calm air all the way up in order to strengthen. Strong wind shear tilts that tower sideways, pulling the top of the storm away from its base and often ripping the entire system apart before it ever has the chance to organise. Picture trying to build a tall tower out of playing cards on a table, with a fan blowing steadily across it. In perfectly still air, the tower can rise higher and higher, card by card. Turn the fan on, even at a gentle setting, and the tower keeps collapsing before it ever gets tall. Wind shear acts exactly like that fan, except instead of playing cards, it is tearing apart clouds, moisture, and rotating air that a storm needs to keep working together. This single invisible ingredient explains why two storms can form in nearly identical patches of warm ocean water, only days apart, and end up with completely different outcomes. One storm might drift into a pocket of calm upper winds and explode in strength within a day. The other might hit a wall of strong shear and simply fall apart, dissolving back into unremarkable rain clouds within hours, as if it had never tried to become anything more. Here is why this matters so much during the current window. El Niño tends to increase wind shear across large parts of the Atlantic, which is part of why this year's overall storm count is expected to run below average. But wind shear is rarely uniform across the entire ocean at once. It comes in patches, stronger in some areas, weaker in others, shifting from day to day, and even hour to hour as upper-level weather patterns move across the basin. That means a storm does not need calm air everywhere. It only needs to find one temporary pocket of weak shear at exactly the right moment, over exactly the right patch of warm water, and hold that position long enough to strengthen before the surrounding hostile winds close back in around it. Forecasters spend enormous effort trying to predict exactly where and when those brief pockets of calm will open up. because a storm that finds one, even for only a day or two, can transform from a minor concern into a serious threat almost overnight. Weather balloons, aircraft, and satellites all feed data into computer models built specifically to track these shifting wind patterns days in advance. Even with all of that technology working together, wind shear remains one of the hardest ingredients to predict with real precision because it can shift meaningfully within a single day. That uncertainty is exactly why a storm's path can look calm and manageable on one forecast update, only to look dramatically more dangerous on the very next one, without a single new storm ever forming in between. This is the invisible tension underneath every forecast issued during peak season. The warm water is already there, easy to map. The wind shear is the wild card shifting hour by hour above it, deciding whether a developing storm gets torn apart while still weak, or left alone just long enough to become something the coastline will remember. A city goes to sleep watching a moderate tropical storm sitting far offshore. By the time that same city wakes up, the storm has transformed into a major hurricane, and there was almost nothing anyone could have done about the timing. This process has an official name: rapid intensification. Forecasters define it as an increase in a storm's sustained wind speed of at least 35 miles per hour within a single 24-hour period. That number might sound modest written out on a page, but in real terms it can mean the difference between a storm that rattles windows and a storm that flattens entire neighbourhoods, and it can happen almost entirely while most people are asleep. Here is how it actually unfolds inside the storm itself. When a hurricane crosses an unusually warm patch of ocean, especially one with deep warm water rather than just a thin warm surface layer, it can pull in energy far faster than normal. Combine that with a brief pocket of calm upper winds, and the storm's internal engine effectively shifts into a higher gear, spinning faster, dropping its central pressure rapidly, and reorganizing its structure within hours instead of days. Picture a top spinning on a table. Give it a slow, steady push, and it spins at a normal, predictable rate. Give it one sudden, well-timed flick at exactly the right angle, and it can suddenly spin far faster than before, almost instantly. A hurricane crossing the right patch of warm water experiences something similar, except the flick comes from nature itself, and the result is measured in human lives rather than spinning toys on a table. This is precisely why rapid intensification terrifies forecasters more than almost any other part of their job. Evacuation orders, road closures, and emergency shelters all take time to organise, often a full day or two at minimum. A storm that jumps from a moderate hurricane to an extremely dangerous one overnight can leave emergency planners racing against a clock that has already run out, forcing decisions to be made in hours instead of the days everyone was counting on. Several of the most destructive hurricanes in recent memory intensified rapidly in the final day or two before reaching land, catching coastal communities off guard precisely when preparation time mattered most. And because this year's ocean carries an unusually large reserve of deep warm water, exactly the kind of fuel rapid intensification depends on, meteorologists are watching for this exact scenario more closely than almost anything else during these 10 critical days, knowing that the next storm to find the right pocket of calm air could transform from a minor concern into a historic threat, in less time than it takes most people to finish a single night's sleep. There is a reason forecasters now issue specific rapid intensification warnings separate from ordinary hurricane advisories, a practice that barely existed a generation ago. As ocean temperatures have climbed over recent decades, this kind of overnight explosion in strength has become measurably more common across the Atlantic, turning what was once considered a rare and unusual event into something meteorologists now have to actively plan for during every single peak season, including the one already unfolding right now. For coastal families, this single fact should change how any warning gets treated during these 10 days. A storm currently listed as moderate is simply a snapshot of one single moment, describing a system that could look entirely different by the time the sun rises again tomorrow morning. Emergency managers have a saying that rarely makes it into news coverage, but shapes almost every decision they make during hurricane season. It takes far longer to move people than it does to move a storm. Evacuating a major coastal city is not something that happens in an hour. Roads have to be reversed to carry more outgoing traffic. Shelters have to be opened, staffed, and stocked. Hospitals have to plan for patients who cannot be moved at all. Studies of past evacuations have found that clearing a large metropolitan coastline can realistically take between 24 and 48 hours, sometimes longer, depending on how many people are trying to leave through the same limited number of highways at once. Compare that against how quickly a modern hurricane can shift its track or its strength. A storm that looked like it was aimed at one state on Monday can be aimed at a completely different stretch of coastline by Wednesday, especially in the days right before landfall, when small wobbles in direction translate into huge differences in exactly where the worst impacts finally arrive. Picture trying to steer a school bus full of passengers away from a fire that keeps changing which direction it is spreading. If the fire moved slowly and predictably, the bus driver would have plenty of time to react calmly. But a fire that shifts direction suddenly, without warning, forces impossible decisions under enormous time pressure, and hurricanes create almost exactly that same kind of pressure for the emergency officials responsible for millions of lives at once. This is precisely why rapid intensification and last-minute track shifts terrify emergency planners more than almost any other part of a storm's behaviour. A hurricane that behaves predictably for days, then suddenly strengthens or turns sharply within the final 24 hours before landfall, can leave officials facing a brutal choice: order an evacuation that might turn out to be unnecessary, or wait for more certainty and risk running out of time entirely. Forecasters have made real progress over recent decades at predicting where a storm will go. Track forecasts today are dramatically more accurate than they were even 20 years ago. But predicting exactly how strong a storm will become, especially in the final day or two before landfall, remains one of the hardest problems in all of weather science, and that gap between knowing where a storm is headed and knowing how powerful it will be when it arrives is exactly where the most dangerous surprises tend to hide. During this particular 10-day window, with warm water capable of fueling rapid strengthening sitting close to the coastline, that gap matters more than usual. A storm forming or strengthening near home, rather than far out at sea, hands emergency planners even less time to work with, turning what should be a careful, well-planned evacuation into a desperate race against a clock that may already be running out. Officials sometimes describe this tension using a simple phrase: the cone shrinks, but the crowd does not. Millions of people cannot leave a coastline in an hour, no matter how quickly a forecast changes. That mismatch between how fast a storm can shift and how slowly a city can actually respond is exactly why this 10-day window deserves attention well before any single storm even has a name attached to it. Ask most people what makes a hurricane deadly, and almost everyone answers the same way: the wind. They picture roofs tearing off houses and trees snapping in half. But decades of official death records tell a very different story, one that rarely gets the same attention. Storm surge, not wind, has been responsible for the majority of hurricane deaths in the United States over the past several decades. It describes a massive dome of ocean water that a hurricane physically pushes ahead of itself as it approaches land, on top of the normal tide, capable of rising well over 10 feet above the usual waterline in the most powerful storms and flooding areas that may sit miles inland from the coast itself. Here is why this particular danger catches so many people off guard. Wind is loud, visible, and immediately frightening, the kind of danger a person's instincts naturally understand and react to. Rising water is quieter and far more deceptive. A storm surge does not announce itself the way howling wind does. It simply rises steadily and relentlessly, filling streets, then ground floors, then entire neighbourhoods, often faster than most people expect once it truly begins. Picture filling a bathtub with the drain closed, except imagine that bathtub is an entire coastal neighbourhood, and the faucet is an ocean being physically shoved forward by hurricane-force winds. Once the water starts rising, there is no draining it away quickly. It simply keeps climbing, filling every low point first, then working its way upward into homes that many residents assumed were safely above flood level. The most dangerous part of storm surge is how deceptively survivable it can look right up until the moment it becomes fatal. Just 6 inches of fast-moving water can knock a full-grown adult off their feet. 2 feet of moving water can sweep away most passenger vehicles entirely, engine, tyres and all, carrying them like toys along a flooded street. Most surge-related deaths happen because people underestimate exactly how little water it actually takes to become lethal once it starts moving with real force, far more than because anyone underestimated the ocean itself. This is why hurricane categories, based purely on wind speed, can sometimes mislead people about a storm's true danger. A powerful hurricane arriving at low tide might produce less flooding than a much weaker storm arriving at high tide, over a shallow coastline shaped in exactly the wrong way to funnel water inland. The wind number on the news might look reassuring. The water pushing towards shore behind that number often tells the far more dangerous half of the story, the half that has quietly claimed more American lives than any other single hazard connected to hurricanes. Coastal geography makes this danger wildly uneven from one town to the next. A shoreline shaped like a funnel, narrowing as it stretches inland, can take a moderate surge and squeeze it into a far taller, far more destructive wall of water by the time it reaches the people living at the narrow end. That single detail explains why two towns only a few miles apart, hit by the exact same storm, can end up with completely different stories to tell afterward. That is why emergency officials increasingly plead with residents to evacuate based on water risk, not wind category alone. A modest storm surge warning, easy to overlook next to a headline about hurricane strength, has repeatedly proven to be the most reliable predictor of where the deadliest flooding will actually happen once the ocean finally starts to rise. A storm too weak to even earn hurricane status once dropped more rain on a single American city than some hurricanes drop across an entire coastline, and it barely made the front page before it happened. That storm was Tropical Storm Allison, and it never reached hurricane strength at any point during its life. Its winds alone would have qualified as little more than a strong summer thunderstorm on most days. Yet Allison stalled directly over the Houston area for days, dumping rainfall totals that reached beyond 30 inches in some neighborhoods, and the resulting floods killed dozens of people and caused billions of dollars in damage, far more than many far stronger hurricanes have ever caused. Here is the uncomfortable lesson hiding inside that storm's history. Wind speed measures exactly one thing: how fast the air is moving around a storm's center. It says almost nothing about how much rain a storm will drop, how slowly it will move once it reaches land, or how much flooding it might eventually cause days after the wind has already died down completely. Picture two garden hoses. One sprays water fast and hard for 30 seconds, then stops completely. The other trickles out water slowly but keeps running for 6 straight hours without ever stopping. Given enough time, the slow, steady trickle can end up leaving far more water behind than the fast, brief spray ever did. A slow, moving tropical storm behaves exactly like that patient trickling hose, and it can flood an entire region precisely because it refuses to move on quickly. This matters enormously for how people should think about storm warnings during the current window. A system downgraded to a tropical storm or even a tropical depression can sound almost reassuring compared to headlines about a major hurricane. But a slow-moving, moisture-heavy storm parked directly over a city for 2 or 3 days can produce flooding disasters that rival or even exceed the damage caused by a fast-moving, far stronger hurricane that blows through in a matter of hours. Emergency officials have increasingly pushed to change how the public thinks about storm danger, moving attention away from wind speed alone and toward a broader picture that includes rainfall, storm surge, and how quickly or slowly a system is expected to move once it reaches land. During this particular stretch of the season, with unusually warm, moisture-rich air sitting over much of the region, that broader warning matters more than ever, because the next disaster along this coastline might not arrive as a powerful hurricane at all. It might arrive as an unremarkable-looking tropical storm that simply refuses to leave. There is a hard lesson buried inside Allison's story, one that applies directly to the 10 days ahead. The scariest word on a forecast map often has nothing to do with the storm's category. Sometimes it is a single, quiet phrase, tucked into the bottom of a forecast discussion: slow moving. A storm that takes its time can end up doing more damage than one that races through and disappears by morning. Meteorologists now track a storm's forward speed almost as closely as its wind speed for exactly this reason. A hurricane moving quickly across a coastline, even a strong one, often leaves in a matter of hours. A weaker storm that stalls, caught between two larger weather patterns with nowhere to go, can sit over the same neighbourhoods for days, turning an ordinary summer rainstorm into one of the costliest disasters a region has ever recorded. Subway tunnels built to survive almost anything a city could throw at them, filled with ocean water in a matter of hours, and nobody watching from street level even knew it was happening until the lights across lower Manhattan simply went out. That night belonged to Hurricane Sandy, a storm that struck the coast near Atlantic City, New Jersey, in late October of 2012. By the time it made landfall, Sandy had technically weakened below hurricane strength on paper, reclassified as a post-tropical system, but its wind field had grown enormous, stretching hundreds of miles across, wide enough to push a massive dome of ocean water toward the entire mid-Atlantic coastline at once, regardless of what any technical category label suggested about its danger. In lower Manhattan, water rose more than 9 feet above the normal high tide level, pouring into subway tunnels, underground parking garages, and the basements of buildings that had stood for over a century without ever seeing water like this. Explosions lit up the sky over a power substation as rising water reached electrical equipment, and within minutes, a huge stretch of one of the most densely populated areas on Earth went completely dark. Here is why Sandy still matters so much to anyone studying coastal risk today. New York City had never been built with a storm like this fully in mind. Its subway system, its electrical grid, and many of its buildings assumed a level of flooding that Sandy simply overwhelmed. The storm caused an estimated $70 billion in damage and contributed to more than 100 deaths across several states, numbers that stunned a region many people assumed was largely protected from serious hurricane danger. Picture a bathtub built to handle an occasional splash suddenly facing a wave large enough to pour directly over its walls. That was essentially what happened to New York's coastal infrastructure that night. Systems designed around historical flooding data that no longer matched the reality of the ocean pushing toward the city. Sandy fundamentally changed how coastal cities across the entire country think about hurricane risk. Engineers began redesigning subway entrances with removable flood barriers. City planners started requiring new buildings in flood zones to place critical electrical equipment on higher floors instead of in basements. Sandy proved, in the most expensive way possible, that a storm technically downgraded on paper could still deliver one of the costliest natural disasters in American history, simply by arriving in exactly the wrong place, pushing exactly the wrong amount of water toward a coastline that never fully believed it could happen there. The most unsettling part of Sandy's legacy is how ordinary the storm looked on paper right up until landfall. It never carried the highest wind speeds. It never earned the most dramatic headlines in the days before it struck. What made Sandy historic was its enormous size, far more than its category number, and the sheer amount of ocean water that size allowed it to push toward one of the most valuable stretches of coastline on the entire planet. Sandy's wind field alone stretched over 1,000 miles across at its widest point, wider than almost any hurricane ever recorded in the Atlantic basin. That single detail mattered more than any wind speed reading, because a storm that enormous pushes ocean water against an entire coastline at once, from the barrier islands of New Jersey all the way up into the harbours of New England, rather than striking just one beach. The wind grew so violent that it physically destroyed the very equipment built to measure it, leaving scientists with a gap in the record that has never fully been filled. That storm was Hurricane Camille, which struck the Mississippi coast in August of 1969, and it remains one of only a handful of storms in American history to make landfall at the highest possible category on the hurricane scale. As Camille approached the coastline near Pass Christian, Mississippi, its winds grew so extreme that every wind recording instrument in the immediate landfall area was destroyed before it could capture the storm's true peak strength. Because of that destruction, nobody knows the exact number for Camille's strongest winds at landfall. Scientists who later reconstructed the storm using modern techniques estimated sustained winds near 175 miles per hour, with gusts that may have exceeded 200 miles per hour, numbers that place Camille among the most powerful hurricanes ever recorded anywhere in the Atlantic Ocean. Picture winds strong enough to break the very tool designed specifically to survive extreme weather and measure it accurately. That single detail says more about Camille's true power than almost any number could on its own, because the storm overwhelmed both the coastline and the scientific effort to fully document how strong it truly became. The ocean itself told part of the story that the broken instruments could not. Camille pushed a wall of water nearly 25 feet high onto the Mississippi coastline at Pass Christian, a storm surge so massive it lifted enormous cargo ships clean out of the water and deposited their crushed hulls directly onto the beach, alongside homes that had simply ceased to exist by the time the storm passed. Camille's death toll reached into the hundreds, split between the immediate coastline and a second, unexpected disaster days later, when the storm's remnants stalled over the mountains of Virginia and unleashed catastrophic flash flooding from rainfall that fell mostly within a handful of hours. For decades, Camille served as the benchmark against which every future hurricane would be measured. The storm meteorologists pointed to whenever they needed to explain what a true worst-case scenario actually looks like along the American coastline. Even today, more than 50 years later, its name still carries weight among people who study hurricanes. A reminder that some storms grow powerful enough to outrun the very science built to understand them, leaving behind more questions about their true strength than answers. Modern technology has closed much of that gap since 1969. Today's instruments are built tougher, and satellites can estimate a storm's strength from space, even if every ground sensor beneath it fails completely. But Camille still stands as proof of something forecasters never forget heading into peak season. The ocean is always capable of producing a storm strong enough to surprise even the tools built specifically to measure it. Survivors who lived through that night described a sound unlike anything they had heard before. Less like wind and more like a freight train grinding endlessly overhead, for hours rather than minutes. Camille rewrote what an entire generation of coastal residents believed a hurricane was even capable of doing to the place they called home, a benchmark that still shapes how communities along the Gulf prepare for the worst-case scenario today. An entire American city sat below sea level, protected by walls of earth and concrete that engineers had promised would hold. Within hours, several of those walls failed, and water simply walked into New Orleans and refused to leave. Hurricane Katrina made landfall along the Louisiana and Mississippi coastline in late August of 2005 as a powerful hurricane, and while its winds alone caused serious destruction across the region, the disaster that followed in New Orleans came from a different failure entirely. The city's system of levees and floodwalls, built specifically to hold back water from nearby lakes and canals, gave way in multiple locations as Katrina's storm surge pushed against them harder than they had been designed to withstand. Water poured through the broken sections and spread across the city for days, eventually covering roughly 80% of New Orleans at its worst point, in some neighborhoods rising high enough to submerge entire houses up to their rooftops. Families who thought they were protected by decades-old engineering suddenly found themselves trapped on roofs, waiting for rescue in a city that had quietly become a lake. Here is what made Katrina different from almost any other American disaster before it. This was a flood caused by infrastructure that failed to perform the exact job it had been built for, far more than simply a storm overwhelming a coastline through sheer force. A betrayal of a promise the city had relied on for generations. Investigations afterward found design flaws, construction shortcuts, and maintenance failures across the levee system, problems that had existed long before Katrina ever formed out over the ocean. Picture a dam holding back a reservoir for decades without ever truly being tested by the worst-case scenario it was designed for. Katrina was that test, and in multiple places the dam failed it. More than 1,800 people died as a direct result of the storm and its flooding, making it one of the deadliest hurricanes in modern American history, and damage estimates reached well over $100 billion. Katrina reshaped how the entire country thinks about hurricane preparedness, emergency response, and the true cost of aging infrastructure sitting quietly beneath cities that assumed it would simply hold when the moment finally came. Nearly 2 decades later, rebuilt levees around New Orleans are designed to withstand far more extreme conditions than the originals ever could. A direct, permanent response to a night when concrete and earth simply were not enough, and an entire American city learned exactly how far that gap between promise and reality could stretch. Katrina's story carries a lesson that reaches far beyond New Orleans alone. Dozens of American cities sit behind similar walls of earth, concrete, and steel today, built decades ago against storms that look nothing like the ones forming over a warmer, more energetic ocean now. Katrina proved that a protection system can look perfectly solid for generations, right up until the single night it finally faces the exact test. It was never truly built to survive. Rescue workers who searched the flooded city afterward described neighbourhoods that had simply vanished beneath the waterline, rooftops poking above brown water as far as anyone could see in every direction. It took weeks before the water fully drained away, and years before entire sections of the city felt anything close to normal again, a timeline most residents never imagined possible in the days before the storm arrived. An entire American island lost its power in a single night, and for some families, that darkness did not end for almost a full year. Hurricane Maria struck Puerto Rico in September of 2017 as a powerful hurricane, carrying winds near 155 miles per hour, just short of the very highest category on the hurricane scale. The storm tore across the island in a matter of hours, but the damage it left behind to Puerto Rico's electrical grid stretched on for the better part of an entire year afterward. Maria destroyed roughly 2/3 of the island's power distribution system in a single pass, snapping transmission towers, tearing down power lines across mountainous terrain that made repairs extraordinarily difficult, and knocking out electricity for all 3.5 million residents at once. It became, and remains, the longest blackout in the history of the United States. Full power was not restored to every customer on the island until 328 days after the storm first made landfall, nearly 11 full months of darkness for some of the hardest hit communities. Here is why Maria's blackout stretched on so much longer than almost any other storm recovery in American history. Puerto Rico's power grid was already aging and underfunded before the storm ever arrived, and repair crews faced a uniquely difficult challenge, since nearly every piece of replacement equipment had to be flown or shipped in by boat rather than driven in on trucks the way mainland disaster recovery usually works. Picture living for months without refrigeration, without reliable running water, without air conditioning during some of the hottest months of the year, and without a single working streetlight after sunset. For hundreds of thousands of people across Puerto Rico, that was daily life, stretching from autumn through an entire winter and deep into the following summer, far longer than any brief inconvenience. The human cost extended far beyond the storm's initial winds and flooding. Researchers studying excess deaths in the months following Maria estimated the true death toll, driven largely by the prolonged loss of power, clean water and medical care, at nearly 3,000 people, dramatically higher than early official counts suggested. Hospitals ran on generators for months. Elderly residents dependent on refrigerated medication or powered medical equipment faced life-threatening conditions inside their own homes. Maria remains one of the starkest reminders in modern American history that a hurricane's true death toll often has very little to do with the storm itself, and everything to do with what happens in the exhausting, overlooked months after the wind and rain have already moved on. Maria exposed exactly how fragile modern life becomes the moment electricity disappears for months at a time, far beyond simply passing through and leaving, a warning that reaches to every coastal community that assumes the lights will always come back on within a few days of the storm finally moving away. Families rebuilt their own version of daily life around that darkness, running generators only for a few hours each evening to save fuel, storing ice in coolers instead of refrigerators, and checking on elderly neighbours who depended on machines that no longer had any power to run on. Maria did not end when the wind stopped. For almost a year, in a very real sense, the storm never actually left at all. A family relaxes on a sunny beach under a clear blue sky, with no hurricane anywhere near their coastline, and within seconds, one of them is being pulled out to sea by a current they never saw coming. This is one of the strangest and most dangerous truths about hurricanes. They do not need to make landfall anywhere close to you to put your life at risk. A powerful storm spinning hundreds or even 1,000 miles offshore can still generate massive ocean swells that travel across open water and slam into beaches on a perfectly sunny, cloudless day, creating exactly the kind of rip current conditions that drown more people every year than almost any other hurricane-related hazard. Here's how it actually works. A hurricane's rotating winds push enormous amounts of energy into the surrounding ocean, creating swells that can travel thousands of miles from the storm's actual center, arriving at distant beaches as unusually large, powerful waves. When those waves break against a shoreline, water gets pushed up onto the beach faster than it can drain back out evenly, and it eventually finds a narrow channel, often near a sandbar or a pier, and rushes back out to sea in a fast, concentrated current. Picture a crowded hallway during a fire drill, where everyone is trying to squeeze through one single narrow doorway at once. Water pushed onto a beach faces the same problem trying to get back out, and when it finally finds a gap, it moves through that gap with tremendous concentrated force, sometimes faster than even a strong swimmer can fight against. This is exactly why rip currents catch so many people completely off guard. There is no dark sky, no wind, no obvious warning sign standing on the beach that a hurricane is even involved at all. Lifeguards along the East Coast have reported people drowning in rip currents generated by hurricanes spinning more than 1,000 miles away, storms that never came remotely close to making landfall anywhere nearby. During the 10-day window at the heart of this story, this hidden danger multiplies. Even if every developing storm out in the Atlantic stays safely out at sea and never threatens land directly, the swells those storms generate can still reach East Coast beaches days later, arriving as deceptively beautiful, powerful waves that pull unsuspecting swimmers away from shore before anyone even realizes a hurricane was ever involved. Lifeguards trained to spot rip currents look for a telltale sign in the water, a channel of choppier, sediment-stained water cutting directly through incoming waves, flowing steadily outward rather than crashing toward shore. Recognizing that single pattern and knowing to swim sideways along the beach instead of directly against the pull has saved countless lives during exactly this kind of invisible, distant hurricane danger. The National Weather Service now issues specific rip current risk forecasts for beaches, separate from any hurricane warning, precisely because this danger so often arrives disconnected from any obvious storm. A beach can sit under a bright cloudless sky, hundreds of miles from the nearest tropical system, and still carry a high-risk rating simply because of swells travelling in from a hurricane, spinning somewhere far out over open water. That disconnect between what a beach looks like and what it actually is doing beneath the surface remains one of the most underappreciated dangers of the entire hurricane season. Miles away from a hurricane's eye, on the side of the storm many people assume is already the safest, a tornado can drop out of the clouds without warning and be gone again within a single minute. Hurricanes are famous for their enormous, slow-moving destruction. Spread out across hundreds of miles over the course of many hours, tornadoes work almost exactly the opposite way, striking a single narrow path with extreme, concentrated violence and lasting only seconds to minutes before vanishing completely. When a hurricane makes landfall, it frequently spawns dozens of these smaller, faster tornadoes hidden inside its outer bands, far from the powerful winds people usually associate with the storm's center. Here is why this hazard catches so many people by surprise. Most public attention during a hurricane focuses entirely on the eye and the eye wall, the most visually dramatic and most heavily forecasted part of the storm. But hurricane-spawned tornadoes typically form in the outer rain bands, sometimes more than 100 miles from the center, in areas where residents may believe the worst of the danger has already safely passed them by. Picture a hurricane as an enormous spinning pinwheel, with individual rain bands stretching outward like long curved arms. Inside those arms, smaller pockets of intense rotation can develop suddenly, spinning up into brief but powerful tornadoes before dissolving again just as quickly. Unlike the tornadoes that form over the Great Plains, hurricane tornadoes tend to be smaller, shorter-lived, and far harder to spot on radar in time to issue an effective warning. This combination makes hurricane-spawned tornadoes uniquely dangerous. A traditional tornado warning in the Midwest might give residents 10 or 15 minutes of advance notice. A tornado embedded inside a hurricane's outer bands often forms and strikes within just a few minutes of first appearing on radar, leaving almost no time for anyone in its narrow path to take shelter before it has already come and gone. Some of the most destructive hurricanes in American history produced dozens of individual tornadoes across multiple states, often causing damage far from where the main storm ultimately made landfall. Hurricane Ivan, which struck the Gulf Coast in 2004, spawned more than 100 confirmed tornadoes across the southeastern United States, an outbreak large enough to rival many dedicated tornado events entirely on its own. During the current window, with storms capable of building unusually fast, this hidden danger deserves real attention. A hurricane's main threat may still be days away from a particular coastline, but its outer bands and the tornadoes hiding quietly inside them can arrive hours or even a full day earlier, catching residents who believe they still had plenty of time left to prepare completely off guard. Meteorologists now treat the outer bands of any approaching hurricane as their own separate warning zone, watching radar continuously for the small, fast-spinning signatures that signal a tornado forming inside the larger storm. It is a strange, layered kind of danger, one storm hiding dozens of smaller, faster ones inside itself, each capable of causing serious damage long before the main event. Most people are bracing for whatever actually makes landfall. Residents in hurricane-prone regions are increasingly taught to treat a landfalling storm as multiple separate threats, layered on top of each other, rather than one single event with one single peak moment. The wind arrives, the surge arrives, the rain arrives, and somewhere hidden inside all of it, invisible until the very last minute, a tornado can arrive too, on its own unpredictable schedule entirely. The wind has stopped, the sky has cleared. Neighbours are already outside cleaning up debris, convinced the worst has finally passed. 2 days later, a river rises without warning and floods homes that the actual hurricane never even touched. This is one of the cruelest patterns connected to hurricanes, and one of the least understood by the general public. A storm can dump staggering amounts of rain across an entire region in a matter of hours, then move on or dissolve entirely, leaving behind what looks like a clear, calm recovery. All of that rainfall drains into streams, creeks and rivers instead, working its way slowly downstream, sometimes taking days to fully arrive at towns located far from the coastline where the hurricane originally made landfall. Here is why the timing catches so many people off guard. Coastal flooding from storm surge typically happens fast, rising and then receding within hours as the storm itself passes through. River flooding works on an entirely different clock. Rainfall that fell on distant hillsides and mountains has to travel downhill first, gathering into larger and larger waterways as it goes, which means the worst flooding along a major river can actually peak days after the sky is already cleared completely. Picture pouring a bucket of water onto the very top of a staircase. The water does not vanish instantly. It spills from step to step, taking real time to travel all the way down before finally reaching the bottom. Rainfall from a hurricane behaves the same way across an entire river system, and towns sitting near the bottom of that staircase may not see the worst of the flooding until well after the storm that originally caused it has already faded from the news entirely. This delayed danger has proven fatal again and again throughout hurricane history. Some of the deadliest flooding events connected to hurricanes happened during the days that followed the storm itself, when rivers already swollen from days of rain finally crested, catching residents who had returned to their normal routines completely by surprise. During the current stretch of the season, with warm, moisture-rich air capable of dumping extreme rainfall totals, this delayed river flooding deserves just as much attention as the storm's initial landfall. A hurricane's most dangerous chapter often has little to do with the moment broadcast live on television while the storm makes landfall. Sometimes it is the quiet, overlooked chapter that arrives 2 or 3 days later, when a river far from the coast finally reaches the breaking point that the original rainfall was always building toward. Emergency officials have started pushing communities to watch river gauges just as closely as hurricane tracking maps during the days following a storm, precisely because that delayed danger has proven so difficult for the public to anticipate on its own. A town that celebrates surviving a hurricane unharmed on Tuesday can still find itself underwater by Friday, once floodwaters gathered from hundreds of miles of rainfall finally arrive at its doorstep. Inland flooding from a weakening tropical system has proven, again and again, to be just as deadly as anything happening along the immediate coastline. Sometimes even more so, because far fewer people living hundreds of miles from the ocean ever think of themselves as being in a hurricane's path at all. That false sense of safety, more than the floodwater itself, is often what turns a delayed river crest into a genuine tragedy. Every single hurricane season, entire towns get built, destroyed, and rebuilt again on some of the most exposed strips of land in the entire country, and almost nobody stops to ask why. Barrier Islands are exactly what the name suggests. Long, narrow strips of sand sitting just off the mainland coastline, formed and constantly reshaped by ocean currents and storms over thousands of years. They serve an important natural purpose, absorbing wave energy and protecting the mainland behind them. But that same exposed position, the very thing that makes them useful as a natural buffer, also makes them one of the most dangerous places on Earth to build a permanent home. Here is the uncomfortable math behind these communities. Barrier Islands often sit just a few feet above sea level, with almost nothing standing between beachfront houses and the full force of an approaching storm surge. When a hurricane strikes directly, these islands frequently take the very worst of the wind, the waves, and the flooding, sometimes losing entire streets of homes in a single night, while the mainland just a short distance away escapes with comparatively minor damage. Picture building a sand castle directly at the edge of the waterline on a beach, right where each incoming wave can reach it. It might survive for a while during calm conditions, but the moment a larger wave arrives, that sandcastle has almost no chance of surviving intact. Barrier Island communities occupy roughly that same precarious position, permanently, year after year, storm after storm. And yet, after nearly every major hurricane, these same communities get rebuilt, often in very similar locations, sometimes with even larger and more expensive homes than the ones that were just destroyed. Government-funded insurance programs, along with the powerful appeal of oceanfront property values, have created a repeating cycle that experts have studied and criticised for decades, one where public money frequently helps rebuild homes in locations that are almost guaranteed to face the same catastrophic risk again within just a few years. This matters enormously during the current window, because a large percentage of the nation's most valuable coastal real estate sits directly on these exposed barrier islands, from the Outer Banks of North Carolina to the beach towns lining the New Jersey shore. A single hurricane making landfall in exactly the wrong spot during these 10 days could destroy tens of thousands of homes built in locations that history has already proven, repeatedly, are simply not designed to survive a direct hit. Coastal geologists have a blunt way of describing this pattern. Barrier islands are not permanent structures, they are living, shifting landforms that were never meant to hold still, let alone hold up a neighbourhood. Some towns have begun experimenting with a different approach entirely, buying out repeatedly flooded properties instead of rebuilding them, and letting the land return to natural dunes and marsh. It remains a deeply unpopular option in many communities, where property values and generations of family history are tied directly to the sand beneath their homes. But as ocean water continues warming and storms continue arriving with more energy behind them, more towns may eventually be forced to choose between that difficult retreat and repeating the same devastating cycle one more time. For now, during this 10-day window, millions of dollars in beachfront property sit directly in the path of whatever storm might still be gathering strength out over the Atlantic, built on unstable, unprotected land, waiting once again to find out whether this season proves too costly to rebuild from. While every ordinary aircraft on Earth is instructed to fly as far away from a hurricane as possible, one small team of pilots does the exact opposite, pointing their plane directly at the most violent part of the storm and flying straight through it. These pilots and scientists belong to a group commonly nicknamed the Hurricane Hunters, and their job is exactly as intense as it sounds. Flying specially reinforced aircraft, they deliberately fly into and through the eye wall of a hurricane, the ring of extreme wind and rain surrounding the calm centre, in order to gather data that satellites alone simply cannot capture with the same accuracy. Here is why this dangerous direct approach still matters so much, even in an age of advanced satellite technology. Satellites can measure a storm's size, its cloud pattern, and its rough intensity from high above, but they cannot directly measure the exact wind speed, air pressure, and internal structure happening inside the eye itself. Only an aircraft physically flying through that environment can gather that information in real time, dropping specialized instruments directly into the heart of the storm as it passes through. Picture driving a car directly into the middle of the most violent thunderstorm you have ever witnessed, on purpose, specifically to measure exactly how strong it is from the inside. That is roughly the everyday reality for hurricane hunter crews during peak season. Repeated flight after flight, storm after storm, often multiple times within a single day as a hurricane approaches land. The turbulence inside a major hurricane's eye wall can be violent enough to toss a large aircraft dramatically, testing both the plane's structural limits and the crew's nerves at the same time. Yet once the aircraft breaks through into the eye itself, conditions often shift dramatically, from violent turbulence into an eerily calm, sometimes sunlit pocket of clear sky, ringed on every side by the towering wall of clouds the plane just fought its way through. This information proves absolutely critical for accurate forecasting. Data gathered directly from inside a storm helps refine computer models, predicting both its future path and its future strength, information that can mean the difference between an evacuation order issued with days of warning and one issued with only hours left to act. During the current window, with storms capable of intensifying rapidly, these flights become even more essential than usual. A hurricane hunter crew flying through a storm today might be the very reason coastal residents receive an accurate, timely warning about a rapid strengthening event still developing invisibly. Hours before, satellite data alone would have revealed the same dangerous change. These crews often fly directly into the same storm multiple times over a single mission, passing back and forth through the eye wall to track how quickly the storm structure is changing from one pass to the next. Pilots have described the experience of breaking into the eye itself as strangely peaceful, a brief pocket of stillness surrounded on every side by the very violence they just fought their way through, before turning the aircraft around and flying straight back into it again. Every dropped instrument, called a drop sonde, falls from the aircraft on a small parachute, radioing back temperature, pressure, humidity, and wind readings the entire way down through the storm. Multiply that single drop sonde by dozens of flights during a single busy week of the season, and hurricane hunter crews quietly become one of the most important, least visible sources of life-saving information behind every hurricane forecast issued along the coast. 22,000 miles above the Earth, a satellite hovers in the exact same spot above the planet at all times, watching a hurricane's every movement without ever needing to blink or look away. These are called geostationary satellites, and their orbit is precisely tuned so that they travel around the Earth at exactly the same speed the planet itself rotates, effectively allowing them to hang motionless above one fixed location on the map, 24 hours a day, without pause. For hurricane forecasting, this unblinking vantage point has become one of the single most valuable tools available anywhere in modern science. Here is why this matters so profoundly. Before satellites existed, forecasters largely had to rely on scattered ship reports, coastal weather stations, and aircraft observations, meaning a hurricane spinning far out over open ocean could sometimes go almost entirely undetected until it was already dangerously close to land. Today, a geostationary satellite can capture a fresh image of the exact same storm every few minutes, creating something close to a continuous, living heartbeat monitor for every developing system across the entire ocean at once. Picture a security camera pointed permanently at one single spot, recording constantly rather than checking in only occasionally. That is essentially what these satellites provide for meteorologists, an unbroken visual record of a storm's entire life, from its very first disorganized cluster of thunderstorms all the way through to the moment it finally makes landfall or fades away completely. Modern satellites carry instruments far more advanced than simple cameras. Some measure cloud top temperatures, helping forecasters estimate how tall and how powerful a storm's thunderstorms have grown. Others measure water vapor high in the atmosphere, revealing dry air pockets that could weaken a storm, or moisture-rich channels that could help it strengthen. Together, this stream of data allows scientists to essentially read a storm's internal condition, almost the way a doctor reads a patient's vital signs. This constant surveillance becomes especially critical during rapid intensification events, when a storm's strength can change dramatically within just a few hours. A satellite checking in every few minutes, rather than every few hours, gives forecasters a genuine chance to catch these sudden changes early enough to issue updated warnings, before conditions on the ground have already become dangerous. During this particular 10-day window, with dozens of tropical waves rolling off Africa at once, these satellites are working harder than at almost any other point in the year, tracking multiple developing systems simultaneously, feeding a constant stream of images and data back to forecasters racing to determine which of these storms, if any, poses a genuine threat to the coastline waiting below. None of this technology existed even a single lifetime ago. Before the first weather satellites launched in the 1960s, a hurricane could form, strengthen, and strike a populated coastline with almost no advance warning at all, discovered only once ships or coastal residents reported it directly. The unblinking eye now hovering above the Atlantic Ocean represents one of the single greatest advances in public safety of the entire modern era, quietly saving lives every single hurricane season without most people ever realizing it is even there. Forecasters sometimes describe this satellite coverage as the closest thing meteorology has to a permanent guard standing watch over the ocean, one that never sleeps, never blinks, and never needs a single day off, even during the busiest, most dangerous stretch of the entire calendar year. Turn on a hurricane forecast during peak season, and you might see something that looks almost chaotic. Dozens of tangled, colourful lines all stretching out from the same storm, each one predicting a slightly different path toward land. Forecasters and the public alike have nicknamed this tangled visual a spaghetti model chart, and despite how messy it looks at first glance, it actually represents one of the most valuable tools in modern hurricane forecasting. Each individual line represents a separate computer model, built by a different team of scientists, using slightly different equations and slightly different starting data, all attempting to solve the exact same impossibly complex puzzle. Where will this specific storm go next? Here is why forecasters rely on so many separate models, instead of just trusting one single, supposedly perfect prediction. The atmosphere is an extraordinarily complex system, and even tiny differences in starting measurements, differences smaller than what any instrument can perfectly capture, can lead to noticeably different predicted paths days later. Rather than gambling everything on one model that might be wrong, meteorologists compare many models side by side, looking for places where most of them tend to agree. Picture asking 20 different friends to guess exactly where a paper airplane will land after being thrown across a windy field. Most of their guesses will likely cluster somewhere in a similar general area, even if no two guesses are perfectly identical. That cluster of agreement is far more useful and more trustworthy than any single friend's individual guess taken entirely on its own. When most spaghetti lines bunch together tightly, forecasters gain real confidence in a storm's likely path, and that confidence gets reflected directly in official forecast cones and public warnings. When the lines spread widely apart instead, sometimes disagreeing by hundreds of miles just a few days out, it signals genuine uncertainty, a warning sign that the situation could still shift dramatically before the storm finally makes landfall. This uncertainty is an honest reflection of how difficult predicting the atmosphere's behaviour truly is, even with today's supercomputers processing staggering amounts of data every single hour. Forecast accuracy has improved dramatically over recent decades, but a hurricane's exact path 4 or 5 days out remains, and likely always will remain, a genuine probability rather than a guaranteed certainty. During the current window, with multiple systems developing simultaneously across the Atlantic, these tangled charts are being generated and updated constantly, every single one representing a team of scientists racing to answer the same urgent question millions of coastal residents are quietly asking themselves right now. Forecasters caution against fixating on any single line inside that tangled chart, no matter how alarming or reassuring it might look on its own. A single outlier model predicting a direct hit means far less than a cluster of otherwise independent models quietly agreeing with each other. Learning to read that agreement, rather than panicking over one dramatic line, has become an essential skill for anyone living through peak season, along a coastline these storms could reach. That is also exactly why official forecast cones exist in the first place, drawn as a widening zone of possibility that grows wider the further out in time the prediction reaches. The cone represents an honest, carefully calculated map of where the tangle of competing predictions currently agrees a storm is most likely headed, rather than a promise about exactly where danger will strike. Two towns sit only a few miles apart on the same stretch of coastline, hit by the exact same hurricane at the exact same time. One is left completely underwater, the other barely gets its streets wet. This outcome might sound impossible, but it happens after nearly every major hurricane, and the explanation comes down to a combination of factors most people never consider until it happens to their own neighbourhood. Wind direction, local elevation, the shape of nearby rivers and bays, and even which side of the storm's centre a town happens to sit on, can all completely change how much water actually ends up in the streets. Here is one of the most important pieces of that puzzle. A hurricane's winds do not blow evenly from every direction at once. They spin in a specific rotation around the storm's centre, meaning the right side of an approaching hurricane, relative to its direction of travel, typically pushes far more water toward shore than the left side does. A town sitting on that dangerous side can face a storm surge many feet higher than a town sitting just a short distance away on the opposite side. Picture stirring a spoon through a bowl of soup near one edge of the bowl. The side the spoon pushes toward gets a small wave shoved directly into it, while the opposite side barely moves at all. A hurricane's rotating winds behave in roughly the same way across an entire coastline, concentrating the worst surge on one side while leaving the other side comparatively calm. Local geography adds another entire layer to this puzzle. A town sitting at the mouth of a narrow bay or river can see incoming storm surge amplified dramatically as the shape of the land funnels water into a smaller and smaller space, forcing it higher and higher as it has nowhere else to go. A neighbouring town facing open ocean directly, without that same funneling effect, might experience a noticeably lower surge from the identical storm. This is exactly why blanket hurricane warnings covering broad stretches of coastline can sometimes feel misleading in hindsight. The underlying physics of wind direction and local geography, rather than any error in the forecast itself, simply produced wildly different outcomes for towns that, on a map, look like they should have experienced nearly identical danger. During the current window, coastal residents should understand that their own specific location within a storm's path plays an enormous role in determining how much danger they personally face, well beyond the storm's overall category alone. The same hurricane capable of flooding one town completely could leave the town right next door largely untouched, and knowing exactly which side of that dividing line you happen to live on could make all the difference in how seriously to take the coming warning. Emergency planners now build detailed neighbourhood-level flood maps for exactly this reason, refusing to treat an entire coastline as a single uniform danger zone. Two houses standing only a short walk apart can carry dramatically different flood risk ratings, one facing near certain flooding in even a moderate storm, the other remaining largely dry even under a direct hurricane strike, simply because of a few feet of elevation difference or a slightly different angle facing the open water. A single number, prominently displayed on nearly every hurricane news report, has convinced millions of people that they understand exactly how dangerous a storm truly is. In reality, that number leaves out most of what actually kills people. That number comes from the Saffir-Simpson scale, the familiar 1-5 rating system used to classify hurricanes by their maximum sustained wind speed. It is simple, memorable, and easy to compare from one storm to the next, which is exactly why it has become the primary way the public judges hurricane danger. But the scale was designed decades ago specifically to measure wind, and wind alone, leaving out storm surge, rainfall, and flooding entirely, despite those three hazards being responsible for the overwhelming majority of hurricane-related deaths in recent decades. Here is why that gap matters so much. A storm rated at only Category 1 or 2, sounding relatively mild compared to the higher numbers, can still produce catastrophic flooding if it moves slowly and carries enormous amounts of moisture. Meanwhile, a storm rated at Category 4 or 5, with extreme headline-grabbing wind speeds, might weaken quickly after landfall and cause less flooding than a much weaker system that stalls directly over a populated area. Picture judging how dangerous a boxer is using only the size of their fists, while ignoring their speed, their stamina, and their strategy entirely. Fist size alone tells part of the story, but it leaves out most of what would actually determine the outcome of a real fight. The Saffir-Simpson scale works in a strikingly similar way, capturing one important piece of a hurricane's danger, while ignoring several others that frequently matter just as much, or more. Meteorologists and emergency officials have pushed for years to shift public attention beyond this single number, developing separate warning systems specifically for storm surge and inland flooding risk, in hopes that residents will stop assuming a lower category number automatically means a safer storm. Progress has been slow, largely because the category number remains the simplest, most headline-friendly way to describe a hurricane's strength in a single glance. This gap in public understanding becomes especially dangerous during exactly the kind of window this story has been building toward. A storm forming nearby, over unusually warm water, capable of stalling or moving unusually slowly once it reaches land, could carry a modest category number while still posing an extreme flooding threat. Residents who check only the number on their screen and nothing else may walk away with a dangerously false sense of security about exactly what is actually heading toward their home. Some emergency agencies have started experimenting with entirely separate warning colours and labels specifically for surge and flood risk, deliberately separated from the wind-based category number, in hopes of finally breaking the public habit of judging a storm's overall danger by one single, incomplete figure alone. Coastal residents who lived through a supposedly minor storm that still managed to flood their street understand this gap instinctively, even without ever reading a single scientific paper on the subject. The number on the screen told them one story. The water rising in their driveway told them a very different one, and it is the second story that history has shown people should trust every single time the two disagree with each other. Most people assume floodwater is simply an inconvenience, something to wade through carefully until it eventually drains away. The truth is far more urgent and far more dangerous than most people ever realise until they are standing directly in it. Moving water carries an enormous amount of hidden force, far more than most people intuitively expect. Just 6 inches of fast-moving water, only about the height of a school lunch tray standing on its side, is enough to knock a full-grown adult completely off their feet. Once someone loses their footing in moving water, the current can carry them rapidly toward deeper, more dangerous areas, often faster than they can find solid ground to stand on again. Here is why this danger escalates so quickly. Floodwater is rarely calm, even when it looks that way from a distance. It typically carries a powerful current, hidden debris, and unpredictable depth changes, meaning a seemingly shallow street can suddenly drop into a flooded ditch or collapsed section of pavement without any visible warning. Someone attempting to walk or drive through what looks like a modest amount of water can find themselves in water several feet deeper within just a few steps. Picture standing in a lazy river at a water park, except instead of a gentle, controlled current, imagine that same pull suddenly strong enough to sweep your legs out from under you entirely, carrying you toward unknown depths filled with submerged obstacles you cannot see. That is closer to the real experience of standing in fast-moving floodwater than most people expect, especially in the initial minutes after a storm surge first arrives. Cold ocean water pushed inland by a storm surge adds another serious risk on top of the current itself. Sudden immersion in cold water can trigger an intense, involuntary gasping reflex, making it extremely difficult to hold one's breath even briefly, a response that becomes especially dangerous if a person is simultaneously being pulled underwater by a current or swept against a submerged obstacle. This combination of hidden force, unpredictable depth, and cold water shock explains why the overwhelming majority of hurricane-related deaths involve water rather than wind. It is also exactly why emergency officials repeat one simple warning again and again, urging drivers never to attempt crossing a flooded road. Turn around. Don't drown. That short, memorable phrase exists precisely because so many people have badly underestimated exactly how little water it actually takes to become genuinely life-threatening once it starts moving with real force behind it. Vehicles add an entirely separate layer of danger to this equation. A typical passenger car can begin floating in as little as 1 to 2 feet of moving water, and once a vehicle starts floating, the driver loses almost all control over where the current takes it next. Emergency responders across the country repeat the same statistic every single hurricane season. More people die in vehicles swept off flooded roads than in almost any other single hurricane-related scenario, a pattern that has remained tragically consistent for decades, despite constant public warnings. This is precisely why evacuation routes get planned so carefully, and why officials close-known flood-prone roads well before water ever actually reaches them. Waiting to judge a road's safety by simply looking at it has proven, again and again, to be one of the most dangerous decisions a person can make during a hurricane, because water rarely announces exactly how deep or how strong it has already become beneath the surface. An order goes out telling millions of people to leave their homes at once, and almost immediately a completely different kind of crisis begins, measured in stopped cars stretching for miles down a single overloaded highway rather than in wind speed. Evacuating a major metropolitan coastline is one of the most logistically difficult challenges any government agency ever faces. Modern highway systems were built primarily to handle steady, everyday commuter traffic, not the sudden, simultaneous departure of hundreds of thousands or even millions of people all trying to leave the exact same region within the exact same narrow window of time. Here is the uncomfortable math behind this challenge. A single highway lane can realistically move only a limited number of vehicles per hour, even under ideal, free-flowing conditions. When an entire metropolitan area attempts to evacuate at once, that limited capacity gets overwhelmed almost immediately, turning what should be a 2 or 3 hour drive to safety into a bumper-to-bumper crawl that can stretch on for 10 hours or more, sometimes leaving evacuees stranded on the highway itself as the storm continues approaching behind them. Picture trying to drain an entire swimming pool through a single garden hose. No matter how urgently the water needs to leave, the hose itself can only move so much at once, and the rest simply has to wait its turn. A coastal highway system faces exactly that same bottleneck problem, except the water in this comparison is made up of real families, running out of time as a storm continues closing in behind them. Some regions have adopted contraflow systems as one solution, temporarily reversing the normal direction of traffic on inbound highway lanes so that every single lane, in both directions, carries evacuees away from the coast at once. This can roughly double a highway's outbound capacity during a genuine emergency, but it requires enormous coordination, significant advanced planning, and enough lead time to safely close and redirect traffic before the roads become dangerously overcrowded. This is precisely why emergency officials plead with residents to evacuate early, well before an official mandatory order is even issued, rather than waiting until the storm feels close enough to finally feel real. Waiting even a single extra day can be the difference between a manageable, if unpleasant, drive to safety and becoming trapped on a gridlocked highway as the storm's outer bands begin arriving overhead. During the current window, with storms capable of intensifying and shifting direction, with very little warning, this evacuation math becomes especially unforgiving. A forecast that looked comfortably distant on Monday can become a genuine, immediate threat by Wednesday, leaving millions of people racing against both a storm and a highway system that was simply never built to move that many people at once. Emergency planners spend the quiet months between hurricane seasons running through exactly this scenario on paper, timing how long different evacuation zones would realistically take to clear under various traffic conditions. That planning matters enormously, but it can only account for so much once real families, real pets, and real last-minute decisions about what to pack enter the equation on an actual evacuation day. For coastal residents watching this 10-day window unfold, the lesson is simple and worth repeating. A highway can only move so many cars per hour no matter how urgent the need becomes, and the single best way to beat that bottleneck is leaving before everyone else on the same road reaches the same decision at the same time. Every hurricane that forms from this point forward is drawing from an ocean that carries more stored energy than it did just a few decades ago. And that single shift is quietly changing what an average storm is even capable of doing. Scientists have spent decades measuring ocean heat content, tracking how much warmth is stored at increasing depths well below the surface itself. Across the world's oceans, including large stretches of the Atlantic, that measurement has climbed steadily over recent decades, driven by the same broader warming trend affecting the entire planet's climate system. Here is why this slow, gradual shift matters so much for hurricanes specifically. Research has increasingly linked warmer oceans to a higher likelihood of rapid intensification events, storms that stall and dump extreme rainfall totals, and storms that hold their peak strength longer after making landfall instead of weakening quickly. Effects that go well beyond simply making storms more likely to form. Picture loading a spring with slightly more tension every single year, so gradually that nobody notices the change from one season to the next. Eventually, when that spring finally releases, it snaps with more force than it would have decades earlier, even though the basic mechanism triggering it looks exactly the same as it always has. Many climate scientists describe the relationship between ocean warming and hurricane intensity in strikingly similar terms. This does not mean every single storm from this point forward will automatically become catastrophic. Wind shear, atmospheric patterns, and simple chance still play enormous roles in determining any individual storm's fate, exactly as they always have throughout recorded history. But the underlying baseline conditions, the raw fuel available to any storm that does manage to form, have shifted measurably upward, raising the ceiling on how extreme an individual storm's peak strength can ultimately become. Researchers studying decades of storm data have found that the strongest category of hurricanes, storms reaching category 4 or 5 strength, appear to be forming somewhat more frequently in recent decades compared to historical averages, even in years where the total number of storms overall remained close to normal. In other words, the most extreme individual storms increasingly appear to be reaching greater peak intensity than similar storms did in past generations, even in years where storms overall have not necessarily become any more common than before. During this particular 10-day window, sitting on top of an ocean already carrying record or near-record warmth in many areas, this long-term trend adds one more layer of concern to an already dangerous stretch of the calendar. A quiet reminder that the fuel available to any storm forming right now is simply not the same fuel that powered hurricanes a half-century ago. None of this means every future storm will automatically become historic, and forecasters are careful never to suggest otherwise. Year-to-year weather patterns, wind shear, and simple chance still decide the fate of any individual system exactly as they always have. But the baseline the ocean now offers every storm that forms is measurably higher than it once was, and that shift alone helps explain why so many of the costliest, most destructive hurricanes on record have arrived within just the last few decades, clustered far closer to the present than to the past. Somewhere along the coast, a hurricane's winds finally reach a substation that has stood untouched for decades, and within seconds, an entire city loses power all at once. Modern life depends on electricity in ways most people rarely stop to consider until it suddenly disappears. Refrigeration, water pumps, hospital equipment, cell phone towers, gas station pumps, and traffic lights all rely on a steady, continuous supply of power running through a vast interconnected grid, one that a powerful hurricane can damage in dozens of places at once, from a single storm passing through. Here is why hurricane damage to a power grid tends to be so difficult and so slow to repair, even for well-funded, well-prepared utility companies. Wind can snap wooden power poles, topple steel transmission towers, and rip lines down across huge stretches of territory simultaneously. Unlike a single localized outage caused by one fallen tree, a major hurricane can damage thousands of individual points across an entire regional grid at the exact same time, forcing repair crews to work through an almost endless list of separate problems, one at a time, often while roads remain flooded or blocked by debris. Picture a spider web with dozens of individual strands, and imagine a storm snapping many of those strands all across the web simultaneously rather than in just one single spot. Repairing one broken strand does nothing to fix the dozens of others still broken elsewhere across the same web, and power cannot typically be restored to an entire neighbourhood until nearly every connection feeding into it has been repaired. For most communities, a hurricane-related blackout lasts anywhere from a few hours to a few days, inconvenient and uncomfortable, but ultimately survivable for the vast majority of residents. But in communities with older, less resilient infrastructure, or in areas where hurricane damage proves unusually severe and widespread, that same blackout can stretch on for weeks, or in the most extreme documented cases, for the better part of an entire year. The danger of an extended blackout extends far beyond simple inconvenience. Without power, refrigerated medication can spoil within hours. Home medical equipment that patients depend on to survive can stop functioning entirely. Extreme summer heat, arriving without any working air conditioning, has proven capable of causing serious harm to elderly and vulnerable residents in the days and weeks following a major storm, sometimes claiming more lives than the original hurricane itself. During this particular window, with a grid already carrying the accumulated wear of an entire summer season, and with storms capable of striking with unusual force behind them, the risk of a widespread extended power failure sits quietly behind every single hurricane warning issued along the coast, waiting for the one storm powerful enough to turn that risk into reality. Utility companies along vulnerable coastlines now stage repair crews and equipment in nearby staging areas before a storm even arrives, positioning trucks, transformers, and replacement poles close enough to begin repairs the moment winds die down, enough to allow crews back onto the road safely. Even with that preparation, restoring power to a badly damaged grid remains one of the slowest, most labour-intensive recovery efforts of any hurricane's aftermath, a race against summer heat, spoiling food, and medical equipment running out of battery power in homes across an entire region. Ask any meteorologist which stretch of the calendar they personally watch most closely, and almost every single one will point to the exact same handful of days unfolding right now. Throughout this entire story, one pattern keeps repeating itself. Warm ocean water, calm upper winds, and a storm's fuel supply all tend to reach their most dangerous combination during this narrow window, roughly the weeks surrounding the peak of the season. It is the direct result of decades of careful data collection, storm by storm, year by year, revealing the same underlying pattern again and again. Here is why this particular convergence deserves more attention than any single storm on its own. Individually, warm water, weak wind shear, and long ocean crossing distances each raise the odds of a dangerous hurricane only modestly. But when all of those ingredients overlap at the exact same time, the way they tend to during this specific stretch of the calendar, the odds of witnessing a truly historic storm climb dramatically higher than they do during any other point in the entire 6-month season. Picture a lock that only opens when several separate keys are turned at the exact same moment. Turning just one key accomplishes nothing on its own. But during this narrow window, nearly every key hurricanes need to become historically dangerous happens to align simultaneously, turning a door that stays firmly shut for most of the year into one that swings wide open for a matter of weeks. This is exactly why forecasters, emergency planners, and coastal communities treat this stretch with a level of seriousness that goes far beyond an ordinary week of summer weather monitoring. Staffing increases at emergency operations centres, additional hurricane hunter flights get scheduled, governors and mayors along vulnerable coastlines review evacuation plans that may not have been touched since the previous year's peak season came and went. None of this guarantees that a storm will actually strike land during these particular 10 days. Many past peak seasons have passed by with the coastline spared entirely, the ocean's fuel and the atmosphere's calm winds never quite finding each other at exactly the right moment to produce a historic storm. But the ingredients required for disaster are undeniably more available right now than during almost any other stretch of the entire year, and that alone is reason enough for the people who study hurricanes for a living to watch this window more closely than any other single stretch on their calendar. Talk to any veteran forecaster during these particular weeks, and a familiar pattern emerges in how they describe their own routine. Sleep grows shorter, coffee consumption climbs, phones stay within reach at every hour of the night, ready for the moment a satellite image or a model run reveals the first real sign that one of these ordinary-looking tropical waves has finally begun to organise into something the entire coastline needs to take seriously. Coastal residents rarely see this quiet, behind-the-scenes intensity, since it plays out almost entirely inside weather offices and emergency operations centres, rather than on the evening news. But it is happening right now in this exact window, at a pace that does not slow down again until the calendar finally carries the ocean past its most dangerous stretch and back toward the calmer, cooler months waiting on the other side of autumn. Somewhere off the coast of Africa right now, a cluster of thunderstorms drifts quietly over open water, unnamed, unnumbered, and completely unnoticed by almost everyone alive on Earth. It may amount to nothing at all. Most tropical waves that roll off the African coast during peak season dissolve quietly within days, torn apart by dry air or unfavourable wind long before they ever earn a name or a single mention on the evening news. Statistically speaking, that is still the most likely outcome for whatever disorganised system happens to be drifting over the eastern Atlantic at this exact moment. But everything this story has traced, the record ocean warmth, the narrow pockets of calm upper winds, the long open runway stretching from Africa all the way to the American coastline, and the 10-day window the entire hurricane calendar quietly revolves around, all of it is currently in place, waiting for exactly this kind of unremarkable cluster of clouds to find the right conditions and begin organising itself into something far more serious. Picture a lottery ticket sitting inside a machine loaded with more winning numbers than usual. Most tickets drawn will still turn out to be nothing, exactly the way most tropical waves still fail to develop, even during the most favourable stretches of the season. But when the odds shift even slightly in one direction, the chances of eventually drawing something significant rise correspondingly, and right now, across the tropical Atlantic, those odds are shifted about as far in that direction as they get all year. Forecasters will spend the coming days watching this system, and likely several others rolling off the African coast right behind it, assigning each one a percentage chance of development, updating that number every few hours as new satellite images and model runs come in. Somewhere within that quiet, methodical process, largely invisible to anyone not actively working in a weather office, this year's defining storm, if one is going to form at all, will most likely take its very first breath. There is no way to know today whether this particular window will pass quietly, adding one more uneventful entry to the long historical record, or whether it will produce the storm people are still discussing decades from now, alongside names like Camille, Katrina, Sandy and Maria. That uncertainty is simply the honest nature of a planet complex enough that even its most closely studied, most carefully monitored weather patterns can still surprise the very people who have spent their entire careers trying to understand them. What is certain is this: the ocean is warm, the upper winds are calm in patches wide enough to matter, the runway from Africa to the American coastline stretches open and unobstructed. Every ingredient this story has traced across the last 32 chapters is sitting in place, right now, waiting quietly for the ordinary-looking cluster of clouds drifting off the African coast tonight to decide what it becomes next. Millions of people along the East Coast will go to sleep tonight without giving any of this a single thought, exactly the way people have gone to sleep every summer for generations. Somewhere out over the darkening ocean, the ingredients this entire story has traced: warm water, calm wind, open ocean, and a 10-day window that only comes once a year, are already gathered in the same place at the same time, waiting quietly to find out what happens next. Somewhere between now and the coming weekend, a decision the ocean has not yet made will decide how millions of people remember this particular summer. Everything traced across this story points toward the same narrow stretch of time. The ocean is carrying more stored heat than it has in years. The upper winds, at least in patches, have opened just enough to let a storm breathe. The long open runway stretching from the coast of Africa across the Atlantic remains exactly the kind of distance that has built some of history's most powerful hurricanes. And the calendar itself, the same 10-day window that has hosted nearly every legendary storm in American memory, is running right now, this week, along this coastline. None of this means disaster is certain. Many years carrying almost identical warning signs have still passed quietly. The coastline spared simply because the final piece of the puzzle, a storm finding the right pocket of calm air at the right moment, never quite came together. That uncertainty is simply the honest shape of a planet too complex for any single forecast to promise a guaranteed outcome, no matter how many satellites, aircraft and supercomputers stand watch over the ocean day and night. But uncertainty is not the same as safety. Millions of people live along a coastline where a single storm, arriving at exactly the wrong moment, has repeatedly proven capable of reshaping entire cities, wiping out neighbourhoods that had stood for generations, and changing the course of countless individual lives within the span of a single night. Camille rewrote what a coastline believed possible. Katrina exposed the fragile promises hidden beneath decades of concrete and earth. Sandy proved that size alone could outmatch any wind speed number. Maria showed the world exactly how long modern life can grind to a halt once the lights finally go out. Every one of those storms began the exact same way this story began, as an unremarkable cluster of clouds drifting quietly over open water, unnoticed by almost everyone who would eventually be affected by it. Somewhere out past the horizon tonight, another cluster is doing the same thing, indifferent to any calendar, any warning, or any person standing on a beach 3,000 miles away. For the millions of people who call this coastline home, the next 10 days carry more weight than almost any other stretch of the entire year, simply because every condition capable of producing a storm strong enough to be remembered for decades is sitting in place at the exact same time, waiting quietly to see what the ocean finally decides to do with it. The window is here. The ocean is watching. The honest takeaway from these 10 days is preparation. The same quiet, practical preparation that lifeguards, forecasters and emergency planners repeat every peak season, whether or not a storm ever arrives. Know the evacuation route before it is needed. Keep a few days of food, water and medication ready without waiting for an official order. Watch the water, not just the wind, and take slow-moving systems just as seriously as fast, powerful ones. None of that preparation guarantees a quiet outcome, but it means that whatever the ocean decides to do with this year's 10-day window, the people living along its edge will meet it having understood exactly what they were facing, rather than being caught off guard by a storm that had been building toward this exact moment since the first warm day of summer.